our own colleague, Gilmore. So most of you know him. He is an assistant professor from the Department of Radiation Oncology, and also he has a joint appointment with our department. So his interest is the development of interactive and interpretable machine learning algorithms and their application in medical research. So now let's give the time to the Gilmore.
Thank you for the introduction, Faye. Does everybody hear me well today?
Yes.
All right, cool. All right. I'm going to talk today about representational gradient boosting. You guys are the guinea pig for this because this is sort of the first time we're going to be presenting this algorithm. So forgive me if I don't, there are certain aspects that you don't get. So just stop me and we talk about the specificities. It's a complex algorithm, it's not simple. So if you do not understand what I'm saying, and certain things are might be controversial, just please stop me there and then we'll just have a debate about it if Aaron let you do it. So, okay, so so briefly, a line of my presentation. So I'm gonna be talking about the analysis of complex data sets, those that include unstructured and structured data, very typical in medicine. I'm gonna first cover the algorithms that are best for the analysis of unstructured data, like images and text. And these are representational learning algorithms or neural networks. And then I'm gonna talk about analyzing structured data, which is and the algorithms that are better for those, which are the statistical learning algorithms, especially gradient boosting, and what to do today when people want to analyze this type of complex data sets, so what type of approach they use. And then after this introduction, I hopefully will be able to motivate why is that we need representation and gradient boosting, what it is. And I'm gonna try to give you intuition of what the algorithm does and why we built it, and hopefully what are these unique characteristics that could be of help to learners of machine learning in medicine. Okay, and finally, I'm just gonna show you some experiments to sort of build up the intuition. So let's go to the meat. So I just here took an example from my own department, and this is how a complex data set for cancer patients are. They are comprised of unstructured data, images like they have CT, MRIs. They also have physician notes, which is NLP, and they have tabular data, the type of data that you can put in an Excel sheet, given by clinical variables and genetic information and treatment, etc., etc. So medical data sets are really, really complex, and of course, to all of this, you have to add time and how this data evolve with time, like sort of time series analysis, missing information, every sort of problem that you could imagine, medical data sets have. So now let's try to go and see what are the best algorithms for the specific aspects and start motivating representation and gradient boosting. So here is an example. It's actually quite telling of what happened after 2012 for the analysis of images. And what you have in the x-axis is just time, and in the y-axis you have the accuracy. And essentially after 2012, the neural networks started outdoing themselves, and every algorithm that was the state of the art at the point was a neural network. Now, these are not common neural networks. These are what I call convolutional neural network. I'm gonna go into explain why this is the case. But for tabular data, the type of data that you can put in an Excel sheet is actually quite different. The top algorithms are gradient boosting or random forest. This is analysis. Here you have an analysis of 150 problems from a public available repository. And what you have in the y-axis is the ranking of the algorithms, how many times the algorithm ends up being the best. So we have this dichotomy of two different classes of algorithms, one that are the best for the analysis of unstructured data, like images and NLP, and one that are the best for the analysis of tabular data, like gradient boosting or XGBoost, which is specific implementation that people use the most. So let's try to dive a little bit more into why this is the case. So to see if we can get some high order understanding of what we can do to maybe bridge these two groups. So first, I just wanted to, by the way, I'm gonna talk for a lot of different audiences here. There are statisticians, biostatisticians, there are also people from my department. So I'm probably not gonna do a good job at for anyone. It's gonna be either too simple or too technical, but I'm gonna try to do my best. So let me talk briefly about neural networks as they were initial neural networks or vanilla neural networks as they were created in 1972. So neural networks are characterized by the transformation of the initial variables, usually linear transformations, followed by a function that is called a link function, that is a non-linear function, and then give you this hidden state that that's what actually is used then later to predict the output, usually using another linear function. Now, neural networks are called or they are a representational learning algorithm because they get the input variables, and these input variables are transformed into a hidden state, and this new representation of variables is the ones that are used to make predictions later on, and that's why it's called a representational learning algorithm. And the way to actually feed the neural networks is using gradient descent on the parameters. And if you use gradient descent on the parameters for a architecture that is a multi-layer architecture, you need to use the chain rule, and that becomes a backpropagation, essentially. Okay. So neural networks have limitations and advantages. I'm gonna first talk about the limitations because I'm gonna spend a little bit more time on explaining the advantages. The main limitations, that's what they gave the initial bad rep in the 80s and 90s, is that they don't do feature selection. They take all the input variables, make a linear transformation, and all of these input variables are part of the finding the representation. If there are bad variables here, the algorithm normally doesn't select them out. Also, they are not, they depend on the scale of the original variables. They are not invariant to monotonic transformations, not the best to handle categorical variables, though there have been a lot of improvement on that to say with encoding and or embedding. And then the last one is quite complicated to handle missing values. So somehow you have to impute them. The advantages really, and this was what it was exploited by a few pioneers like Yang and Hinton and Benjo that kept working on them, even though that they were not popular in the 90s and early 2000s, is that they are modular. And this then, because what do I mean by modular? That you have all of these channels. And because you have these channels and you're learning them using backpropagation, then you can input a lot of prior information into them. So let me show you, for instance, an example. When people talk about convolutional neural networks, they say neural networks are better for images. But these convolutional neural networks are very different from the original networks. And they have a lot of prior knowledge that has been put into the form of functions to make them perform well for this specific task, which is classification of images. So now I just want to try to give you a very fast overview of how a convolutional network works, so that you sort of understand why is that they perform better than other type of algorithms for the analysis of images. So here to your left, you have a regular neural network, and to your right, you have a representation of two layers of a convolutional neural network. And the way that convolutional neural network work is that they take the initial 3D image, and it's a 3D because you have a layer for each color. So these are color images. And then what you do is that you have these filters that you're gonna sweep through the image, and that's what you're trying to find. Now I'm gonna illustrate this in the next slide, but just I want to give you the idea of what they're trying to do here. In images, it's quite important locality. A pixel next to another pixel is half information. So sort of creating these very local features that then get combined as architectures get deeper to have a deep, more complex feature down the string, sort of matches what is believed to be the function to classify this type of, or humans use for this type of tasks. Also, another important thing is being invariant to translation or transformation. Like if you rotate your head, you're sort of the same person. Same with a cat, for instance, if you're classifying cats. But somehow your classifier needs to capture that. It doesn't matter if the pixel change the value in the locality, it still is sort of the same classification, okay? So how do they do that? Okay, can you see the gift here? Do you see it interactively?
Yes.
All right, so what is happening here is that you have these filters, that this is what the network is finding, and the filter is just a tensor, a 3D matrix that multiplies the original image, and then when you multiply the original image, you start swapping it and add all of the values, and then you get these new values, right? So these filters are at the beginning, because you're saying, give me the filter that maximizes some sort of information. Try to find general features. Actually, it's been shown that these initial convolution filters, they just look like lines or circles, things like that. But as you progress, they get more complicated. And you could also use the modularity or the multi-layered architecture of networks to introduce invariance to translation and transformation. How? For instance, you could say just, you get after you transform the original pixels, which are given here in these columns, you could say, well, I'm gonna get the maximum of this matrix. And the maximum means it doesn't matter if the pixel shows up in the center or into one corner, you still get sort of the same value. So what I'm trying to say here is that the fact that convolutional neural networks work better for images might not be related to the statistical conditions of the algorithm, but to all the prior knowledge that was given to them. That's very different for the statistical learning algorithms. For the statistical learning algorithms, or the one that are trying to use to analyze Excel data, if you take, for instance, age, and you move it from the first column and you put it in the fifth, there is no knowledge gained or lost. So there, the statistical characteristics of the algorithm sort of matter a little bit more, because you're saying that there's not information to be gained from the structure of the way that you got the information. So here matters more certain other characteristics, like, is the algorithm performing feature selection? Is it able to fit nonlinear functions? Is it invariant to monotonic transformations of the initial variables? Or are they able to automatically handle the missing information? And how easy it is to regularize them? Now, there is an algorithm that satisfies most of these, except for a big one, which is number 5. And those algorithms are simple vanilla decision trees. The way that the original decision trees work is they do brute force search through all the variables, and they find the variable on the partition that maximize certain information gain. So they do intrinsic feature selection. They are able to feed nonlinear functions. They do not depend on monotonic transformation of the original variables, invariant to them, and they are very capable of handling missing information. However, they have a huge drawback, which is very hard to regularize. And they end up overfitting. We have done a little bit of work on helping that with the additive tree, but the general algorithm, like cards, sort of suffers from this. So if you look at now to the one that work, the algorithms that work better for the analysis of Excel tabular data, these two actually use tree-based models as their base learner. So there are ensemble method that combines a lot of them, and using tree-based models as the ensembles. Now, these algorithms, what they do is that they take the advantages of trees, but they try to mitigate the disadvantage, which is regularize the function better, give more control to the user so that you do not overfit. Now I'm gonna try to talk and explain gradient boosting, and I hope I don't do a bad job. This algorithm was introduced in 2001. It's today consistently #1 winner in CAL competition for Taula data. In one of their versions, it's called GBoost. So let me just give you a little bit of a description of what gradient boosting does, because it's going to be very important when I motivate a representation of gradient boosting. So gradient boosting is trying to obtain a function that is going to be an additive function, a sum of functions. And they do that by writing an original loss function. And once you write the loss function or the empirical loss function as a function of your training data, for known x's and y, this is a functional of f. If you actually start that f as a constant, and then if you make small changes to that function, you could see the effect on the loss function and just treat it like if it was a variable. So you could do, by the way, I'm doing a lot of hand waving here, but what you can do is to find the generalized residual, which is just the derivative of the loss function with respect to the function that you want to obtain, and start fitting that residual in this step here. And this is just of doing gradient descent in the step of functions. So every step that you take it to minimize the loss function by finding the direction of the gradient of the loss function, and then you are fitting them. If you actually do that using trees, then you end up with a summation of trees, and you take all the advantages that trees have. But this allows you to regularize it better, because essentially you can decrease using the step size or a smaller step size using the shrinkage parameter, how much influence each of the trees that you're adding to the function bears. Now, funny enough, and we could ask Jerry about it, this is, I felt in love with this explanation of gradient boosting, but this is the know-how, for instance, Jerry actually explains it. So, okay, so let me start moving from here. Now we have this dichotomy of having one type of algorithm that is the best for the unstructured data like images and NLP, and another type that is the best for the tabular data. So what to do if your data set like ours contains both? So there are many approaches. For instance, you could give the tabular data to a neural network. The neural network have channels, but then you're going to force the neural network to analyze these Excel features, the ones that you can put in a cell sheet, like the structured ones, and it is not the best for that. Also, you could give the images to gradient boosting, but it's not the best for that. So normally what people do is what they call stacking, is that they feed these functions independently. They take the images and they feed the neural network to the outcome. Then they take the tabular data, they feed the neural network, the gradient boosting to the tabular data, and then they linearly combine these two models, right? This is called stacking or blending. The problem with this approach, and this is, by the way, the most important point of the talk, is that when you are feeding independently these models, they don't know that you're going to combine them later. So they end up overfeeding or learning things or a structure on the data they don't need to, because they will have been explained by the older models. So this approach is inefficient. And we had this hypothesis that maybe if you actually figure out a way to train them both at the same time, neural networks and gradient boosting, then you might do better. And that was one of the motivations of gradient boosting, of the representation of gradient boosting, although this one came very late, to be honest. We didn't start researching these aspects until last year, and it has taken like 3 years to do this algorithm. So, okay, now let me jump into representation of gradient boosting. By the way, until now, any sort of questions? Okay, cool. I guess let me now jump to what representation of gradient boosting is. Well, in representation of gradient boosting, what you're going to do, you assume that you have a multi-parametric, a multi-layered function, like a neural network, where this function is a function of functions, but different from neural networks, you're not going to assume any specific functionality from the basis. but you're actually gonna estimate them. So for instance, you could say, my function, my general function is a function of O and functions of all of these representations, okay? But I don't know what they are, so I'm just going to try to estimate them by putting them into a loss function and creating a mechanism that allows me to find O, F1, F2, Fk. Why to do that? Because if I can do that, then I could have these sort of channels where I could put in one of them a neural network, and I could put another one a gradient boosting. And then what the O does is learn them together and optimize them, knowing that they're gonna be combined instead of having them individually built. And hopefully that is gonna offer some advantage. Also, as you can see, each of these channels is a non-parametric consistent estimator. So by themselves, they're allowed to fit any function. So one of the original questions we had was like, okay, so if we have these non-parametric functions here in the channels and in the output, can we recover the underlying nested functions if that's the data generating process? And that's another thing that I'm gonna sort of investigate here. Okay, so what I'm going to do now that you have sort of the general framework of what representational gradient boosting is trying to do is to walk you through the algorithms. Then I'm gonna talk about some specific experiments that we did to build out the intuition, and then I could open it to questions. So first, I'm gonna talk about what is the formalism to obtain this non-parametric neural network, if you wanna see it this way, or obtain a representational gradient boosting, which is how we see it. And then investigate the merits of that new type of function. Now, there are three types of ways to create a new algorithm in machine learning. Either you have a new loss function, a new function, or a new optimization methods. I guess representational gradient boosting has two. It has a new class of functions, and then that class of function invokes a specific optimization algorithm, which will be backpropagation in the space of functions. And I'm gonna try to cover all of that, and that will be the formalism. And then after that, sorry, I'm gonna talk about what are the type of conditions that we need and specific scenarios to be able to recover the data generating function if the data generating function is a nested function. And then I'm gonna give you very specific intuition of when representational gradient boosting works and what are the type of problems that actually are best suited for its type of architecture. Okay. Now, this is probably the most complicated slide in the whole talk. So I'm just gonna try to, I don't pretend you guys understand everything here, but I'm gonna try to give you a flair for the pseudocode of how you can actually obtain these general functions on each of the layers and in the output, right? So let's start by just investigating what you could call as a vanilla representational gradient boosting, which is just one layer, even though representational gradient boosting can also be written with way more than one layer, but I'm gonna make a comment after that, after I talk about this. So, okay, so we have one layer of representational gradient boosting, and now we want to estimate O, and we want to estimate the Fs. I'm not assuming a specific functionality for them. They're gonna be general functions. Okay, so the first thing, if you assume that the Fs are known, the way to estimate the output is just gradient boosting, because the Fs transform the original X's, and now you just want to find O in the as a function of the Fs, but not of the original X's, right? So this is just gradient boosting here. Now, once you have an estimation of O, if you want to estimate the Fs, what you have to do is to backpropagate the residual back, but in the space of functions. Because here, we are not moving in the space of parameters, similar to gradient boosting, we are moving in the space of functions to make the updates that are typical of gradient boosting. And this is what it does. I don't know if you guys recognize this term here, but it's essentially the LDO, the ODF, which is the generalized residual or the first derivative of the loss function respect to this nested function. Okay, and it's just the chain rule, and it becomes a backpropagation in the space of functions. So with these two blocks, you could actually start performing updates. You can make an update for the output function, you could make an update for the bases, and then start growing their complexity. Now, I just want to make a point here. Note that different from neural networks, just because I'm not specifying a class of functions in the basis, their complexity grows with every step that I make, okay? So I do not depend on having the right architecture as much, because each of these functions by itself, as you take steps, increase on complexity, and then they can describe more complex functions. Now, we haven't investigated that yet, but that's one in the to-do list, meaning can we reduce the size of the networks if we actually have these complex nodes? Okay, so with this sort of overview of what gradient boosting, representational gradient boosting does at the algorithm level, and hopefully you just get the idea, let me try to walk you through the intuition of the algorithms and experiments to actually justify those intuitions. So I got, yes.
Will you get a chance to describe how well it's converging on a number of problems you've studied?
Yeah, I'm gonna go into that now, Olivier.
Okay.
In order to do that, I'm gonna investigate 3 classes of functions that they sort of cover different aspects of the task we wanted to achieve. The first one was the very simple one, which is just a linear function. The output function here is gonna be linear function of the basis and the pairwise interaction terms. Okay. The second one is a linear combination of the bases here, and we're gonna use this one to compare to stacking, being able to say whether if you grow them independently or together, you improve that model. And the final one is the more general version of implementation, where essentially the output is a summation of ReLus. And what we're gonna be investigating here is how, if these hidden layers help the networks train better, and at the same time, this final implementation, because both the outputs and the bases are non-parametrics, then they are gonna be able to fit any sort of class of functions. So we could ask, okay, can we recover nested functions, et cetera, and the different parts. Okay, so now let's start using these functions to gain intuition of how representational gradient boosting works and what is its main contribution at this value. So first of all, I'm gonna show you synthetic data and also real experiments. The reason for synthetic data is because we really control the data generating function. So we can actually gain a lot of insights on how the algorithm is working. But of course, the argument against not synthetic data is, well, does that type of problem exist in reality? And that's why you also have to have real data sets. And we're gonna show both. Okay, so for the synthetic data sets, we build this nested function, which is just main terms, and then the pairwise interactions with noise that had mean zero and variance that depends on the experiment, and I'm gonna tell when it does. Now, what are the bases? The bases are, the first two were taken from the original Jerry's Freeman regression data set. That's F1 and F2. And the F3, we just made it up so that it has a similar feeling to it, okay? Now, if you know that something very specific, these functions have up to 2 other interaction terms. But when you multiply, because of these multiplication terms, then you introduce many, many more interaction terms. Every multiplication is essentially, you get all of these terms and you multiply by the other one. So there are up to 55 interaction terms in this very simple function. And that will be one recurrent topic in our presentation from now on, is that these nested functions or functions of functions have usually many interaction terms, okay? And also the order of the interaction increases as well. And the synthetic data, by the way, is a function of 15 variables. Each of these channels is function of 5. Okay, remember that, that's also gonna be important. Okay, So the first thing is that we wanted to investigate is, okay, if we give prior knowledge to our algorithm, can we, perform better? And what prior knowledge that is? Okay, well, we know that the variables can be grouped together. So we can give the right first 5 variables to the first channel, and the second 5 variables to the second channel, and the third 5 variables to the third channel. And, try to get a function that is closer to reality that way. Or we simply can give the 15 variables to all the channels and run it this way and see what happens. Okay, what do you think? Anyone want to take a guess of what would the result be? What model will work better?
To all the channels.
Exactly. I wish I had understood that, because we spent a year, and I'm not joking, just trying to see what we were doing wrong. I should have talked to whoever answered the question, which is way smarter than me. So
thanks about that.
So this is what happens. If you actually force the function to build the right functions to a single channels, you perform worse than if you give all the variables to all the channels. So I'm going to give you the intuition of why that is, and it took us a long time to understand. But actually, interesting enough, both models perform better than gradient boosting. Okay, so let me tell you the intuition why is that if you give a function to all the channels, if you give the variables to all the channels, you perform better. There is something that is a very common topic in statistics that is called identifiability. When you have two functions, and especially nested function, you're gonna say that a function is identifiable if saying that they are equal also means that the parts are equal. Like if this function here is equal to this, that means that O is equal to T, F is equal to G, etc., etc. Now, that is not true for nested functions. There are many ways that you could get the same function, either learning it through O, learning it through O, or learning it through F1 or F2 or Fk. So by forcing this function to only use these 5 variables here, you are sort of forcing it to go to a very specific region of the space where each of these functions are learning the right one. Now, that reduces variance because you are reducing the number of hypotheses that this space of function has, but can also make it more difficult for the whole overall function to find the right target, because you don't necessarily, to approximate Y properly, you don't need to build F1 or F2 or F3 correctly. You just need that the whole combination is right, okay? And Faye, that introduced me here, has some theorems on the paper that we're gonna publish soon about this, which are quite interesting. But essentially, this is sort of the important breakthrough that we had, which is nested functions are tricky. Intuition doesn't necessarily work. Forcing them to go to something that you think should be, just because they are not identifiable, doesn't mean that you're gonna get there, okay? So let's try to sort of see what's going on, and if we could tell the,
Helmer, can you go back to the last slides, or just a quick question? Are these subsample of your inputs connected in any way? Are you balancing them in any way relative to the features, or it's randomly separated?
Which layer, Olivia? What can you specify?
The input where you have your vector X for the input feature.
Exactly. So the input is original this function, right? These 15 variables: x1, x2, x5, x6 to x10, and then x11 to x15. So those are vectors. Now, either you could group them into these groups, 1, 2, and 3, like what we do here, group 1, group 2, or group 3, or you could give all of them to all the channels. The problem is that if you group them, then you are forcing this function here to go to the right specific function. And that can be harder. you are reducing variance, but you are giving less capability of algorithm to actually get to the right one. Now, this was in variable of even putting noise, putting extra features, etc., etc.
So the question, I think, is if we are pre-processing those variables, I guess.
No, they are generated between 0 and 1, randomly generated, and then we give it through this function. So nothing, we're not doing anything to them. What do you mean pre-processing? I don't understand, actually. I guess I don't understand the question.
They're all independent.
They are independent, yes.
I have a question. This is Jean.
Hi, Jean.
Hi. Wait, so are you summing up the outputs of the base function just for to get the actual output? Because aren't there interactions between each of these?
No, this is the output is non-parametric. We are using the neural RGB. So,
okay.
Both the first layer and the second layer is non-parametric. So if there are interactions, the output should learn it. And that's the thing, right? You can learn, because you have non-parametric functions in all of these functions, you can learn the final function through many different ways. You don't have to learn it through learning the RIF1 and the RIF3 and then learning the RIO. There are many combinations. There are many combinations of them that could give you the final answer.
Okay, got it.
Yeah. So let's try to understand what's going on more. So let's do more experimenting, and many of these things are going to become apparent of what's going on right now. So the first thing is like, okay, you know, intuition is, oh my God, intuition is not working. If I provide prior knowledge, it doesn't work. And let's clarify, no. The problem is that you are misspecifying the output function. If you actually specify the correct output function, meaning you know what the output function is, then you could actually reverse. Then providing prior knowledge helps. And actually big time. Here is the difference of error between the not providing prior knowledge versus providing prior knowledge. And the reason is that not only you can do that, but you could actually recover the basis. You could recover F1. Here you see if you provide the output, the right output, then the algorithms recovers the F1. But if you don't, then very weak correlation of F1. So the problem is that because the output in our original experiment is misspecified, then there is no way that this thing starts walking to the right function. The basis and the output go to wherever they want, okay? So now a natural question would be, okay, if I provide prior knowledge to the output, could I actually recover it then? And say how much prior knowledge I need to provide to do that. So what we did here is that instead of feeding the algorithm to the original X's, what I'm gonna take is the real F's, the output of the basis that I know, and then feed it to an output and initialize an output that way by feeding it different amounts of percent to the right Y, but using the true basis. And after I do that, then I have an initialization that is very close to the right function, and then I let it work wrong again, and I see when I actually can recover it. Unfortunately, the results were also negative, meaning even when I feed in the output to 95%, it's still forcing them to walk towards the right solution, harm performance. And only improved when I was, we were feeding them to 99% of the original function. So what this means is that recovering nested functions is not only impossible theoretically, but it's a very hard problem in practice. And the other implication is that because intuition really doesn't work for nested function, we need to be very careful when we say that an algorithm is working better than the other, because we offered prior knowledge. And that prior knowledge, because of the nested function, might not be moving your function to where you want it to be. And that was really important to us, especially if you analyze neural networks. Okay, so
Gilmer, I have a quick question, if that's okay.
yes, sir.
For the NRGB, I haven't looked at this enough, but you could tell me very quickly. You can't write out your original generating function with the pairwise interactions in the form of a neural network by setting certain weights to 0.
Well, it is. If I put the output as the interaction ones, it is a neural network too. But there I'm defining the real outputs. With NRGB, you are trying to estimate this, right? And this is the problem. When you are trying to estimate this function here, then the algorithm will get lost because you don't have the right basis to start with, or you don't have the right output to start with. So the whole thing starts walking to a different point in the space where it doesn't necessarily recover the right underlying function.
Oh, okay, I think you just said it was like misspecified, and I was wondering how you could say that if it could be represented.
It can be, but you're not starting it with the right function. So that's what I mean, misspecified. Okay, I understand what you're saying. Yes, if you actually feed it enough, you could recover. It's not misspecified in that sense. It's a misspecified in the sense that is not you are not starting it at the right function. So they're gonna walk together to a different point on the space, but not necessarily to the right function.
Okay, thank you.
All right. Okay, so now this is very important because again, it tells you how difficult it is to have intuition about these prior knowledges in nested functions, that they have all of these walking parts. Now, regardless of this, both versions of NRGB outperform gradient boosting in this particular problem. So let's try to understand why that is, okay? And the key is these terms, the interaction terms. If I remove them, look at what happens. Gradient boosting becomes the best algorithm. So essentially, by removing all of these interaction terms, you go from the NRGB being the best to gradient boosting being the best, okay? Now, this tells us a lot of why representational gradient boosting and in what type of problems it actually works best. So let me spend a little bit more of time on this. Remember that when I add these interaction terms here, I'm putting a lot of high order up to 4th order interactions into my function, even though that is only 3 terms because they are multiplying together. So it's true that both gradient boosting and NRGB can fit these functions in general because gradient boosting is a consistent estimator, but RGB does it way more efficiently. In RGB, if you add an stump to these bases, then they get multiplying the outputs to build the higher order terms. And because they get multiplied, every stump that you add to the bases implies many more interaction terms in the output. Now, for gradient boosting, in order for it to actually discover high order interaction terms, they have to be main effect terms that are important. Because remember that the trees are greedy by nature. So first you have to, in order to discover the structure of this tree, you have to have a tree that is interaction term that is important at the single level variable, and then discover the second one. And if you keep increasing this, then it becomes less likely to be discovered. So what I'm saying here is that what representational gradient boosting offers over gradient boosting is that by making these very simple partitions, like only one here on the basis, it can discover high order interaction terms because the output is multiplying all of them, or finding interaction terms, versus gradient boosting that sort of prefer the main interaction terms because they need to exist in order for you to discover the high order one, given the greedy nature of the trees. Right? So up to now, the first two things. Unfortunately, we cannot discover a nested function, and that was a true bummer because I wanted to use RGB for gene analysis and pathways and things like that, and we could talk about it later. But it does offer a unique value, which is a representational gradient boosting, like all representational learning algorithms, is really good at discovering interaction terms efficiently because it's sharing all of these parameters through the structure. Okay. So this is just summarize what I just told you. So single storms can model high order interaction. In gradient boosting, that doesn't happen. Okay, so up to now, intuition is tricky because of identifiability problem. Although prior knowledge can work, it's definitely no guarantee. And RGB outperforms gradient boosting in problems where there are many high interaction terms. Okay. If that's the problem is not like that, then you get the opposite. Okay, so now the application that I think is gonna, like the hook, what is the most important part is, can you actually gain something by optimizing the functions together instead of optimizing them differently? So for this experiment, what we're going to do is that we know that trees are really good at modeling interactions, but bad at modeling linear models, and vice versa, linear models cannot model interactions. So we're gonna get the data, the same data, and we're gonna fit the linear model, and we're gonna fit the gradient boosting and then linearly combine them using stacking, versus growing this function, the same output function, so it's the same class function, but the bases are being optimized together using representational gradient boosting. And when you actually do that, you obtain a positive results, as you would expect, meaning optimizing the bases together outperforms optimizing them separately and then combining them. Now, this is something that is very unique to representational gradient boosting, and it's a really, really neat application that, of course, needs to now be tested with way more models, etc. But essentially, you should expect that if you optimize them differently and independently, you're gonna outperform, perform worse than if you actually optimize them together, knowing that you're gonna combine them. So this opens up to, you know, having in one of the channels a neural network, convolutional neural network, and then in another channel for the tabular data having gradient boosting, and then just growing them together. So probably this is the most important practical contribution of representational gradient boosting. Okay, and now let me just give you a real data set example, and then just open it up to discussions. In this real data set example, we have a make brain signal. I'm going to tell you what that is now. And this is a time series problem. And we thought that time series are particularly nice for representational gradient boosting because it has all of these channels, and then they get combined to have an outcome, and then you could input prior knowledge through the modularity of the algorithm, etc. Okay, so what we have in this experiment is 90 channels or sensors, and each of them have 180 observations that are depending on time. So we split the data, taking the 80% time points, and then putting apart the 20%, and then testing the algorithm. Now, what is the make signal? Well, this is a magnetoencephalography, and what it does is like the neurons, when they are firing, they emit electric currents, and that electric current has a magnetic field, and the device just detects that magnetic field through the head, and then this can be used to detect what parts of the brains are related to each other, and if there are dead parts that should be activated but they are not being activated, and then use it clinically to perform surgery in that region, etc. So there are many ways you could use MEG data. And now let's tell you how to analyze or use representational gradient boosting to analyze this type of data. Well, just because it's a time series, by itself, that time series actually offers you a way to use the modularity. You could get, for instance, let's say that you define the lag, and you say, I'm gonna predict the value, next value using the last 5 data from all the sensors. So you could have the general version where you send all the data regardless of time to all the channels, or you could say, well, let me separate the data because I feel like data from recent time matters more than all the data from time that where time has passed way more. Okay, so that's what it's essentially doing here. So you have lag 5, and then to one channel you only send one type of data time before, and so forth and on. And then you could also do like a specific regularization. You say, the farther away you are from my prediction, then the more regularization I'm gonna have on you, because you're gonna influence less. Okay, all of these are direct results of having this modularity that is a really important property of the algorithms like representational gradient boosting or neural networks. Okay, and let me just give you the results here for this experiment. And I also want to say that we compare to gradient boosting and LSTM models. So LSTMs are the type of neural networks that actually analyze time series data. As you can see, initially, if you don't provide any information to representational gradient boosting, it does worse than regular gradient boosting. But once you group the variables by time, and you actually input the learning rate differentiation between the different channels, then RGB with all of this prior information becomes the best algorithm, and especially outperforms also the neural networks. So now what this means is that feature selection is very important. Remember, these LSTMs and deep LSTM don't have intrinsic feature selection in them, but all the other algorithms do have intrinsic selection. In the paper that we're going to publish, there's another example using NLP data, but I think this is a really good illustration of what RGB can do. Essentially, it can offer feature selection to multi-layer architecture functions like the type of ones that neural networks fit. And now conclusions, to open it up to discussion to everybody, is essentially that with representational gradient boosting, we are allowing gradient boosting to have the modularity that neural networks have, and providing at the same time neural networks with 3 base layers that allows them to perform feature selection and not being depending on monotonic transformations, and also increase their complexity as with every iteration, not depending on having a deeper architecture, or not as dependent on having a deeper architectures. And finally, which is probably the most important practical results, especially for medicine, is that you can do optimized stacking, which is that you build the different channels together, knowing that you're going to combine them with the output function instead of building them independently and later combine them. So I want to now really thank my co-authors. So Jerry, Stanford, and Faye and studies in our department here at UCSF. So there's an overrepresentation of biostat departments for RGB. And just leave this as a points of discussion, and happy to take questions.
Thanks, Gilmer. I was just wondering on computation time with representative gradient boosting.
It's a complex algorithm. So each of these channels is a gradient boosting channel. So you need powerful computers, but something that can be handled today.
Hi, Gilmer, it's Aaron. Whenever you talk, I always have about 5 questions, but I'll try to keep it more limited. For those results where you were comparing accuracy, I couldn't quite catch as you were going through it. You were scaling like the best performing model.
Yes.
Percent, because I'm just wondering about the magnitude of the difference in these errors.
Oh, it depends on the problem specifically. I could give you that later, but essentially I am scaling them to the best performer.
So you know, when you look at something like ImageNet, we have accuracy, so we can clearly compare, and I get the improvement in certain models versus others. But here, I mean, I am interested in the magnitude. Is it? I know it was case specific, but in the 2 examples you just presented, is the magnitude difference in the errors between these different approaches that large?
The magnitude becomes more important for the real problem, right? Because the synthetic data is telling you one related to the other. In the real problem, the magnitude is actually quite big. I could give you the numbers. I don't have them here. But you're right, around magnitude also matters. When you are testing an algorithm against the other ones, I guess relative error it's important to compare them, but yeah, you're absolutely right. Magnitude of the difference matters. could give you those results later. I just don't have them here with me.
And then my second question is, when you're pouring all the data in at the beginning, I assume if you're putting in something like a neural network and some unstructured data, are you going to still do a little bit of curation in terms of how the data enters the model? Like you might have both tabular data and image data flowing into a neural network, but you probably won't have imaging data flowing into a tree-based method?
Exactly. So the idea would be, let's say that you could, one of these bases, I guess this is what I put here. One of these bases just get the input of the images, and one of these bases get the input of the tabular data, and then you just start optimize them together.
Yeah, I think this is a very important point because people can put a bunch of data into a neural net, you know, covariates, imaging data, and add in a linear component, and the linear component for the tabular data does nothing. It's hard to know,
exactly,
what's being picked up on in the neural net that might actually be part of the linear model. So I think delineating the contributions of these additional tabular data is that's an important thing that I'm glad you.
Funny enough, now that you're saying it, everybody highlights that as the most important contribution of RGB. We didn't build it for that reason, but yeah, it's apparent that's a very important portion of it. The fact that you could actually segregate these classes of functions and see the contribution of each of them and optimize them together is quite important. And then you can optimize differentiable and non-differentiable functions like gradient boosting together with differentiable functions like the neural network. Is very important. So I agree with you.
Hi, Gilmer. This is Miok. You mentioned that the one of the disadvantages of the neural network is that it's not doing the feature selection. So
yes,
in your gradient boosting, so ideally, I'm expecting that so you are sort of like the basic features axis actually includes that the non-essential one, and then sort of your gradient boosting algorithm is essentially sort of based on that some complex functional form we might not know, but only sort of involving that the important features. Like, so what is that the feature selection component of that you are gradient boosting?
Okay, that's a good question. Thank you for asking. Okay, remember gradient boosting is using tree-based models, right? As the base learners. So let's go to the tree, this here. Just bear with me a sec. Okay. So the tree-based models, they go through all the features and they say, is this feature important? Yes, then it makes a partition. It only chooses one, and then so forth and on. So trees by itself intrinsically offer feature selection. So if your function is a summation of trees, you are selecting features. You're not letting all of them be part of the model. So gradient boosting has intrinsic feature selection built in when you use tree bases. And that is inherited by representational gradient boosting if one of these channels is gradient boosting. Does that answer your question?
Yes, only partially, but the rest of it, I have to think more about it.
Oh yeah, it's a complex algorithm.
Because the thing is that I see that your nice presentation of the intuition about the nested functions, but at the end of the day, we don't really need to know that whether F is nested in O or what's nested in the other. It's just that what more gets into that which features matters and what is the sort of the relative degree of the impact on the Y, right? As long as I can compute some sort of the gradient, and as long as that this algorithm is selecting that the features, I may not really care about exactly how it's done.
There might be instances, yes, I agree with you that if you only care about prediction, then you don't care about the right inference. However, the original motivation, for instance, or even the original idea about RGB is not what I'm telling you today. We wanted to hopefully use these to discover pathways, and each of these bases was going to be a pathway. And for that, you do care about the inference, and you care about the functions that get in each of these pathways and which genes are related to each other and things like that. So there are instances that you might care more about just the final Y prediction, and you care about the parts. Unfortunately, it's impossible to do because you never know what the output is or the basis. But originally, we wanted to do inference on on nested function. The problem is because of the identifiability, it seems that the level of prior knowledge that you need to input is too high, unfortunately. But what I'm trying to say is that there are cases that you might want to, or you actually care about the different parts. You just not only care about why. Victor, you were going to ask a question?
Yeah, Victor Conos here. So I was thinking a bit more of a bit higher level as a practitioner, maybe. I like the fact that you have some unstructured data on one side and then structure on the other side, and try to blend them. So I was thinking, like, you know, usually one way of blending is to use another neural network on top of that to blend those two together. So the question is, how would that approach compare to your model itself? Like, is there like a significant gain in accuracy or whatever? Or
significant will depend on the problem, but that's exactly the point. See, when we blend in here, we are using a neural network. This is using, when you're blending the algorithm, you could use here an output function. For instance, the key to your question, Victor, is today, when you're blending, you build these models independently of each other, right? You have, let's say, gradient boosting, and then you have a neural network, and then you blending after, okay? With a representational gradient boosting, you can blend them using whatever output you want, let's say a neural network. But when you start building them, you're gonna build them together knowing that they're gonna be blended, so that the imaging part or the neural network part doesn't go and learn the things from the tabular data. And vice versa. So
I got that conceptually. What I'm thinking is, like, with a data set, like, can we compare them directly? Like, one is a lot more accurate than the other.
Okay, now this needs to be researched. That's a valid point. What we did here, blending a linear model and a tree, and we, by the way, chose it smartly because trees are very different to linear models. These are the results. And I will have to go back and check the magnitude, which goes to Aaron's questions. Now, that question needs to be investigated now. We need to get very complex data sets, hopefully medical data sets, and that's going to be next, putting a channel, a neural network, putting a channel of the tabular data, and build it together and see. It's gonna be problem dependent, right? There are gonna be problems that's gonna be a huge winner if there are like interaction terms between the tabular data and the images, because you really need to know that the others exist to use them. And there are problems that they are completely independent and it doesn't matter. You could actually build them separately. So it will be problem dependent, but for the ones that you have interactions between the tabular data and the, let's say, the image or NLP, then this offers a very unique way to build them together, and say it should be more accurate.
Good.
Hey, Gilmer, I have another question. Since we're talking about the sRGB and you're on the slide, you presented the formula with some weights for each function.
Yeah.
So are those weights identifiable, and have you thought about ways to put constraints on them so that this model could perhaps tell you of the channels that you're considering which are the most important for this problem?
It's actually quite interesting, and that's, by the way, Aaron, really deep question, and we could spend an hour talking about it. I know you told me that every time that we talk, you have like 5 questions. Okay, so let me give you a really smooth answer, and then we take it offline, and we address this question properly because it's a very important one. So yes, you could put regularization to this type of things, so that every step that you do feature selection on the. Okay, so let's talk about it. If the channels have different complexity, once you are doing the output step, the coefficients are going to be more geared toward bringing the functions that are more complex, right? Because those are going to correlate more with the outcome. So you need to put some sort of regularization to avoid that. And yes, you can do that. To your answer of identifiability, if the bases are different, meaning one is a tree and one is a linear model, let's say, then already the models are identifiable. They are different. But then you need to take into account the fact that one might be more complex than the other, and then you need to, if you want them to have equal strength, you need to penalize one more than the other, which can be done with the learning rate parameters, these ones. But we can take it offline, I think, and give you right stuff on sort of a deeper question. But I don't know if it satisfies your question in a general sense.
As long as you promise to talk to me later about it.
I promised.
Are there any questions? So one question that, I mean, what is the biggest data set you have been handled?
Here is a 10,000 points, right, Stathis? When you perform the experiments?
Yeah, that's right. Well, the training was, I think 7% of that, but yeah, the whole data set started at 10K.
So for this type of data set, how many hours it takes?
It doesn't take too long. It entirely depends on the number of iterations. And again, one of the good things is that, yes, it's a complex model, but you will also converge sometimes, depending on everything, much faster. We have all these learning rates, of course, complexities, but with neural networks, people are used to many epochs, right, which take a very long time. You can actually learn pretty fast. Always data set dependent.
There is a trade-off between learning fast and generalizability. So it's a complex algorithm. Meaning, yes, it is complex. It's as complex or more than a neural network, because each of these channels is a consistent estimator, and it's a non-parametric, so it's growing in complexity. So it's not a simple algorithm. So it has computational restrictions, especially when we are comparing massively in many experiments. Instead of just, like, let's say, pick one problem and optimize it for that, then it becomes a challenge because you have to run like many experiments in many type of functions, etc.
Is there a lot of hyperparameter tuning?
No, this is actually one of the advantages of it compared to neural network. It has the same amount as gradient boosting, meaning 3. Learning rate, depth of the tree, number of steps. Now, this is actually a really important question, because the complexity doesn't matter. You don't need to really specify the structure. You could always, even if, okay, the simplest version of representation and gradient boosting is only one channel and the one in the output. That would be gradient boosting. And that is already a really powerful consistent estimator. So the algorithm doesn't depend as much on the hyperparameters. The most important one is the learning rate, but you know, depth of the tree. Actually, in all the experiments that I showed you, I never fine-tuned the hyperparameters for RGB. The other algorithms had hyperparameters fine-tuned. So it's very not as much dependent as other type of models like neural networks, for instance, which really matters. The architecture matters more and things like that. But again, all of these answers are empirical answers, right? I'm sure that you can find a data set where you had to actually have to search.
Okay, any other questions? No. Thanks for our speaker.
All right. Thank you, everybody.